First of all, thanks again for taking the time to talk to us here at the HLF, and congratulations on your win of the ACM
Thank you.
Prize in Computing. To start off with, tell us what you received the award for.
Yeah, so the ACM Prize in Computing Award was a recognition of the last 10 to 15 years of research that I've been working on. So it actually includes the work that I've been doing around computing and sustainability and computing in healthcare. So it includes the work that we've done in terms of energy and water monitoring, and then also some of the more recent work that I've been doing around mobile healthcare.
So let's go back a little bit.
Okay.
What was your degree in? How did you get into the area that you're into, and what interested you in the first place?
Yeah, so my degree is in computer science. And so even though my formal degrees are in a bachelor's in computer science and a PhD in computer science, I've done a lot of work in hardware as well. So I could have double majored in electrical engineering and computer science, but I mainly have a computer science degree, but did a lot of work in sensors and hardware as well. So I'm actually a professor in computer science and electrical engineering. So I have a double appointment at the University of Washington. But yeah, it's in computer science. In particular, I looked at the area of human-computer interaction within computer science. So looking at more of the applications of computing to to new interfaces, new interaction technologies. But quickly in grad school, I realized that I was much broader than that. So my research really pulls on different aspects of computing. So it could be machine learning, it could be sensors, it could be networking, distributed systems. It's really kind of a confluence of a lot of different areas in computer science. So it's hard to put a finger on one thing that I do, but it's really around the intersection of sensors and machine learning is kind of the core of what I do.
So after you graduated, let's say you got your bachelor's, and then you went on to a master's?
A PhD, actually.
So your PhD.
Yeah, so I didn't do the master's, yeah.
And where was that?
That was at Georgia Tech. So I started at Georgia Tech with my undergraduate degree in computer science. I was actually pretty lucky because in high school, I took a lot of AP and IB classes. And so when I joined the undergraduate program at Georgia Tech, I already had pretty much sophomore status. So I was only an undergrad for 2.5 years, and pretty much the entire 2.5 years I did research. So I kind of knew I was going to go down the research path when I went into undergrad, and so I did research as a freshman all the way through. And then when I graduated, I remained at Georgia Tech to continue the research momentum as a PhD student.
And just to clarify, AP is advanced placement,
yes,
and BI is
yes,
IB.
AP is advanced placement, and IB is international baccalaureate,
which are both American high school programs.
Right. The international baccalaureate program is a program that's actually an international program. So it's basically getting a degree at the high school level that is commensurate with any high school degree across the world, actually. So it's basically level at the same level of any other high school. So if I wanted to go to a university outside the U.S., that would allow me to level set with other universities.
Okay, so you got your PhD from Georgia Tech, and then what happened?
So I got my PhD in Georgia Tech in 2008, and so pretty much right after I became a professor at the University of Washington in computer science and engineering and electrical engineering. So right when I graduated, I got a faculty position right after. So.
And I should mention that you and I talked then because I did an article that included a lot of quotes from you for Communications of the ACM at that time.
Yeah.
And as I remember, it was about energy sensing and water sensing, and maybe you could tell us a bit about that.
Yeah. So a lot of my work that I did as an undergraduate, was a lot of it was on home sensing and looking at applications of home technologies. And then in grad school, I really pushed the boundaries in terms of new sensing techniques. And so I applied some of that work, actually a lot of that work towards sustainability. So looking at how do you use sensors in the home to monitor activity. I actually adapted to looking at how do we monitor energy usage and water usage in the home. And that was a lot of the work I did as a continuation as a professor early on. And so some of the work the work that was we discussed in the communications at ACM was kind of that applied nature of the work I was doing. So a lot of that, and some of that work actually spun out as a company that got acquired by Belkin in 2010. So which was around energy and water usage using sensors and machine learning to be able to disambiguate where you're using water or electricity so that you can provide actionable feedback to homeowners in terms of what they can do to save energy use. And if they do, you can actually give them a real-time feedback on how they could actually save energy in the home. So.
Now, the company you spun out, what was the name of the company?
It was called Zensi.
And did it get a name once it went to Belkin? Or
Yeah, so Belkin has a bunch of different product lines. So there's the Wemo product line. So that was part of the home automation work that they were doing, became part of that. And then Belkin actually spun out another company within Belkin called Finn. So Finn is actually commercializing all the water work. So you can buy technologies from them, which basically tells you when there's a leak in the house, where water is being used. It'll actually turn off your water if there's in case of an emergency. It knows that it's regular water usage versus a leak. And so being able to kind of conserve water that way. And then Belkin has a set of projects or products that integrated some of the energy monitoring into their Wemo product lines as well.
And I remember what I found fascinating about your work then was that you weren't directly measuring the devices.
Right.
If you could describe how that sort of
Yeah,
worked.
so some of the things we did was looking at indirect ways of monitoring energy usage. Because the idea was that at the time was, one way you could do this is put a sensor behind every appliance. So you could put a sensor behind your toaster, your oven, your dishwasher, washing machine. But if you think about the number of electrical devices in your house, there's just so many of them that you just can't practically instrument all of them. And some of those devices, how do you get behind a oven? You got to pull the oven off the wall. And so we actually looked at ways that you can put one sensor in the house and indirectly identify energy usage. So what we found was that every time you use an appliance, there's electromechanical interference or electrical noise that's propagated over the power line, and that's just the side effect of using an appliance. And so we actually monitor that signal and try to disambiguate and infer, was that a dishwasher? Was it a washing machine? Or was it a TV or a light bulb? And we do the same thing for the plumbing system. So instead of adding a sensor behind every water fixture, we have a single pressure sensor that you could screw on a hose bib potentially. And then we look at the water patterns that are changing, the pressure patterns, to say, that looks like a toilet flush versus a dishwasher that just turned on, or maybe a faucet.
Now, you mentioned machine learning in this.
Yeah.
Is it supervised? In other words, do you have to say, does it say, now flush the toilet and I'll see what you did?
Yeah, a lot of the original algorithms were supervised, so you have to label it or train it. So basically, hey, flush the toilet a couple of times, now it's learned that pattern. Turn your TV on and off, it's learned that pattern. But one of the things that we saw was that some of those patterns are kind of generalizable. So, there's only so many ways you can manufacture a toilet flapper valve, right? And so that time series signal kind of looks the same across different toilets. The home's geometry and the layout of the plumbing does change the signals a little bit, but we did find that there are some signals or some labels that are generalizable. So if you train it in one house, you could potentially apply it in other houses. So you can actually label it. So for example, if somebody labels an Xbox, that signature could be labeled for other people. So you can actually crowdsource the labeling as well. So there's many different ways of doing it where one person's labels that, it comes up as an unknown device and you label it as an Xbox, it actually has labeled it for everybody else too. So you can use those techniques as well.
That's really cool. Yeah. So after you sold that off to Belkin, what did you do next?
So I kind of continued this kind of line of work of looking at the applications of computing for different kind of high impact areas. So one area that we looked at was kind of continuing in the home automation space and looking at, hey, what are the other pain points? So the initial pain points we tried to solve was how to reduce the number of sensors in the house so you can make it practical to deploy, was that, there's just some things that you can't indirectly sense, right? If you're going to build a carbon monoxide detector, or if you're going to detect a sensor that detects, certain kinds of events in the house, there might not be an indirect way of sensing it. So in that case, you do have to put lots of sensors in the house. And the example I always gave was, people have smoke detectors that have batteries in them, and they don't even replace the smoke detector batteries, which is a life-saving device, and that thing is beeping in the middle of the night. And so that's like 4 or 5 devices you might have in your house. But if you have 10, 20, even 100 devices, it's not practical to replace all those batteries. So we wanted to go down a path to develop a way that you could reduce the power requirements of these IoT sensors in the home so that you don't have to worry about replacing the batteries of these things that often. In fact, make it low power enough that you could potentially use wireless power technologies in the future. And so that's where we built this device called Snoopy Technologies, which was basically a way of kind of similar in spirit to the first line of work, which was using the existing infrastructure for sensing. Here what we said was, could we use the electrical wiring in the house as a large antenna? Because you got wiring in the walls anyway, and so we built this sensor that would communicate with the electrical wiring in the walls wirelessly, and you'd have a base station that was plugged into the wall. So you only need one of these base stations. And so these sensors would actually chirp at a very low power because you only need a couple to the closest wall, and there's walls all over the place. So in traditional Wi-Fi, you have to get that signal from your device all the way to the base station, which could be on another floor, it could be many walls away. And so you need to actually increase the energy output. But for this approach, you just need to increase the energy output just so that it gets to the closest electrical wire. And there's electrical all over the place, right? And so that allows us to build a platform that was so low power that, to do temperature, humidity, leak conductivity testing, like if you can use a water leak sensor, would last about 25 years on a low coin cell battery. That was so low power that it would last forever almost. And so that's what we worked on for a few years, was creating a general purpose platform to enable a bunch of different sensing approaches there.
Has that been applied to smoke detectors?
So right now, smoke detectors are actually there's two versions. There's wired versions of those and battery powered versions of those. So right now it hasn't been applied to smoke detectors, but it could. But what we did apply it to was temperature humidity sensors for mold. We've actually applied it to other sensors. The reason why smoke detectors are difficult is because the wireless isn't the main issue. The sensor in a smoke detector is actually power hungry. So the power consumption is actually dominated by the sensor in that case. So we applied it in places where there was already innovation in some of the low power sensors, and where the wireless transmission was the bottleneck. That's where we've applied it to. So. And
that was something that you did after Belkin, right?
That's right. Yeah, that was a consumer product called Wally Home was the name of the product, and then the technology underlying it was Snoopy. And so that technology was acquired by Sears Holding Company to kind of embed into their appliances and different products that they were offering.
Okay, continuing on. Yeah. That's not the end of the story, as I understand.
No, it's not. Yeah.
So what happened next?
So we continued kind of this notion of leveraging existing infrastructure. That's kind of been the theme, right? Initially it was existing electrical and plumbing to monitor energy usage, existing electrical to be able to use it as a wireless signaling technique. So then actually along the way, we've actually already been dabbling in healthcare. Healthcare is one of those things you got to start. It takes a long time to kind of innovate in that space. So in parallel, we were already looking at this concept of leveraging mobile phones for screening a diagnosis. So the idea is that the ubiquity of the phone and the fact that there's already amazing sensors on the phone, how do we use those sensors that are being used for telephony, gaming, and other use cases? How can we adapt them for physiological monitoring? So how do we take these amazing sensors that are just getting better and better for healthcare? And so one of the first projects we did was looking at adapting the microphone for helping people with asthma monitor their asthma. Basically, the idea is that how do you measure lung function? So just like how you would go to a cardiovascular, going to a cardiologist to get an echo or a EEG reading, the equivalent device in the pulmonary space is called a spirometer. It's a device you blow into. It's kind of a big device that you go into the clinic to use. They make home spirometers as well, but the problem is that you might not have this with you when you need it, when you think you're having an asthma attack. So we actually wanted to build a clinical grade spirometer into a phone without having to have any additional hardware at all. Just use the microphone. So the idea here is, again, leverage an existing ubiquitous platform that if you can make that work, you can disseminate this broadly very rapidly. And so we adapted that kind of line of work and used the microphone for a bunch of projects, for cough detection, for spirometry. We started to use the camera and flash for a bunch of different things, everything from hemoglobin assessment, so using the camera and flash as a way to see the minute color changes in your blood without pulling blood out of the body, just through your finger to assess how much hemoglobin is in the blood, kind of like what you would do with a blood draw. We did things around jaundice assessment for babies, where you take a picture of the baby to figure out how much bilirubin's in their blood. We did something around analyzing the pupils for concussion analysis as well. So looking at the constriction and the dilation of the pupil when somebody thinks that they're in a concussion scenario to see if they're actually concussed or not. Things also trying to potentially screen for pancreatic cancer using the sclera of the eye to see how much minute amounts of yellowness that's being appearing. So looking at ways that we can use phones for screening has been another area that actually now a lot of people have started to build off of. So there's this whole field around mobile health, which is using phones as sensors, not just data collection tools. In the past, people were using phones to collect data. Oh, I'm going to journal my what I've eaten, or I'm going to journal my data that I've collected from a glucose monitor or my external spirometer, but actually using the phone to collect that data. And that's now the whole field has come up in terms of using the phones for diagnosis now.
Now, it does surprise me that the color differentiation would be good enough for the applications that you suggest. What were some of the challenges for that?
Yeah, a lot of the challenges is that if you take a traditional approach at looking at how do you screen for some of these things, then it's really hard to do that, because you want to look at, well, what is the underlying signal that you're looking for, right? So in terms of a blood analysis, you have an assay or blood chemistry that you're trying to adapt for, and so the challenge was finding an optical analog. Right, so a lot of the work that we have to do is innovate on alternate ways of getting the same signal, and the other thing is to recognize you don't have to be perfect, right? The goal isn't to have an alternative to a blood draw, because you can never really have an alternative to a blood draw. But what you can have is something that's close enough that you can use it as a screening tool to get it out to people sooner, so that you can alert them on when they need to do the blood draw. Right? So by the time you do the blood draw, it might be too late. So looking at how do you build screening tools. And then the other thing is that if you can do it often enough, then what really matters might not be the absolute number, but the trend. So if my hemoglobin tool was off by a little bit, it might not matter, because what I care about is I'm taking a reading every day, or maybe once a week, and look at my trend, and that trend might be the indicator to say, go get a blood draw. So that was the other recognition that, look, you don't have to make it perfect. Let's get it as good as possible. But what are other uses for that? But in that case, we found that there was an optical way of doing that, because hemoglobin is composed, blood is composed of water and hemoglobin, and then the different frequencies of light absorb and reflect hemoglobin. And so we knew what that was. You can actually study what the optical properties of hemoglobin are, and then it turns out that the white flash on a phone is broadband enough that you just pick out the blue or the red band. So what we were riding on was that mobile phones are getting better at doing photography, right? If you use a modern smartphone, the image you can capture is amazing, but what we can piggyback on is the fact that you have amazing lighting and amazing imaging sensor that you can use it for healthcare now. So we're piggybacking on that innovation as a side benefit.
And what kind of error range do you have for such senses?
Yeah, so some examples include, actually, a fascinating one is some of the spirometry work that we did was that
That's the breathing.
The breathing one, yeah, where you breathe into the phone without an attachment to give you your lung function. So if you have chronic asthma, it tells you your lung function. So how much air can you breathe out over a certain amount of time? It turned out when we did those studies that they were actually close to the gold standard, which would be the clinical device. In fact, close enough that it could be used as an alternative to a home spirometer. And so some of that work we're actually going through the FDA with is close enough that you can actually get FDA clearance for some of these things.
Wow.
The hemoglobin app in particular, they make a non-invasive device like that. So it's not a phone, but it's a device that you clip onto your finger. And it turns out our device is actually pretty close to that. So I mean, you're seeing accuracies that might be a correlation of 0.90, like 90% correlation, which might be good enough for screening. In fact, might be good enough for primary diagnosis at some point as well. So we're getting to a point where some of these things can be FDA cleared, and some of which we're actually pursuing.
So it seems to me that there's two things happening here.
Okay.
One of them is in order to develop such things, one is the conceptual idea. Okay, I'll get the signal a different way from what everyone else is thinking.
That's right.
And the other is the actualization.
Yeah.
Maybe if you could talk about both of those procedures and how they fit together.
Yeah, and both are very difficult, and it's kind of interesting how you approach it, because one is working with our clinical collaborators and our health experts, but tackling it in a different way. Because if you talk to a clinician or a health researcher, the way that they would tackle the problem is how they would look at it, right? The way you capture blood pressure is with a brachial cuff. But it turns out we use a brachial cuff to get blood pressure because that's kind of the gold standard right now. But it turns out that's actually not the most accurate way of doing it. If I cross my legs or if I cross my arms, you're going to get a different result. The right way of getting it is to actually catheterize somebody, but that's pretty invasive, right? And so if everything that we develop, you have to compare it to the brachial cuff, it's not the perfect standard, but that's kind of the kind of the de facto right now. So you have to kind of think out of the box a little bit to say, well, what are the other signals that are correlated to it? Even if the community quite doesn't believe that that's the right way to do it or don't buy into it because they're not used to it, then you have to validate it. So that's one of the challenges in healthcare is that if you're trying to think out of the box, it's going to take some time before it gets adopted because it's not trained in residency, it's not trained in med school. Like a lot of experts might not have the right mental model to adapt to it. And so that's the one thing is trying to think out of the box. You've got to really think differently because if you're trying to go non-invasive, you have to do it in a different way. So it's really a collaboration with the clinical experts, medical experts, also students that have a little bit of a bioengineering background too. So they understand the physiology, they understand some of the things that a sensor can do. And then the implementation is that it's really hard to build some of these things. Like to create an application that can turn a phone sensor into a camera sensor that's so sensitive that you can get these minute changes is tough. That's a lot of engineering that happens too. So often as a researcher, the engineering you often don't get credit for. It's like, oh, you're not doing research, you're doing engineering. But what I would argue is that the engineering is what enables you to answer these important research questions. So it's really tackling the problem of, am I solving the right problem? Is there a need to have a non-invasive tool on a phone? If there is, well, what are all the different ways I could solve it? Try those research paths, and then at the same time, oh, by the way, you got to engineer something that nobody's ever built before, and then you could do a clinical trial. So these are long-term research investments. That you can't just do this overnight. The students are prototyping, iterating, prototyping nonstop, and collecting clinical data to validate it. Which is most computer scientists. This is not your normal world, right? You're not in the clinic and prototyping and building. A lot of times, you might already have a data set. The data set might already be validated by the research community. Here's a data set that every computer vision researcher has to validate their algorithms against. We don't have that. And so it really requires a unique way of approaching these research problems that most computer scientists don't really think about it that way. So, but those are the big challenges is you got to collect the data and you got to build those systems to be able to actually interpret the data.
So you mentioned students, and in your press conference earlier today, you also mentioned a lot of interaction with students.
Oh yeah,
and that sort of brings us around to the HLF.
Okay,
which, as you know, is the laureates like yourself and the young researchers. Let's talk a little bit about sort of how you were mentored as you were coming up, and what helped you.
I've been lucky to have great mentorship everywhere, all the way through. Middle school, junior high, where actually in my junior high we actually had a technology education program, which was kind of rare in Alabama to have a tech ed program at the middle school level. So I was actually really got into technology early, but had good mentorship there. And then in high school, great mentorship because we had a great computer science program. And then when I got to undergrad, my thesis advisor in grad school was my actually undergraduate advisor too. So I ended up staying in the same research lab. But my thesis advisor, both on the undergraduate and on the research graduate side, really took on a lot of freshmen. So I started doing research as a freshman. So he would actually invest his time into really junior students to be able to mentor them, to be able to be confident on how to do research. But the thing that really helped was that he never tried to adapt me into his research, like his research mindset, right? He was really well known for having a broad set of students he would graduate. So my thesis advisor, Gregory Abel, is known for having students that have a background in ethnography. He's graduated everything from ethnographers to me. I'm on the other side of ethnography. And the way it is, he teaches his mentees to, how to do high quality, rigorous research, but really empowers them to be able to do what they're great at. And so that's one of the things that he saw that, that I'm really passionate about hardware and the applications of hardware to computing. And he basically created an environment to let me thrive in that space. He really didn't have as many students that had my kind of interest before I started working with him, but now he's actually taken on more of those kinds of students, right? But he created that environment, that creative environment. And so I kind of learned from him in terms of how do you create an innovative group is you don't micromanage the students. You let them flourish by creating an environment for them to do the creative work, right? And let them and figure out what their passions are and adapt this research around that. Because the students are going to work their best and the hardest, and they're going to be the most motivated on working on the things that are personally motivating to them. Right? And so you have to find what that is in that student and try to mold that program around them. And so that's what I've learned a lot on how to do. But it's really the environment. I can mentor them, I can give them as much advice as possible, but it's really creating an environment that can actually allow them to flourish is the most important thing.
One thing that the young researchers see in the laureates is they see people who are already successful.
Okay.
And it's sometimes hard to imagine them going through difficulties.
Right.
So how do you advise your students when they come across difficulties, when they hit a wall?
Yeah, that's a great question. I mean, and that's one of the challenges of any graduate program. You have these ebbs and flows. You have these times where things are going great, and then you have times that, then where you hit a wall where paper doesn't get in, you hit or you're trying to solve this problem and just can't quite get past the problem. And so you have, and one thing I often tell students is that, hey, if you're a graduate student, and which is a lot of those students in the HLF program or undergrads looking at grad school or doing research, is that at least you're hitting these walls under the safety of the university, right? Just think about it. You have a problem, but you have an amazing set of resources around you to be able to get past that problem. A lot of students run into problems in the real world, but if you're running into the problems as a grad student, you have a framework around you to help you get through those set of problems. And I think recognizing that you have mentors, you have colleagues, you have other students that you can lean on to be able to brainstorm or look at other alternative ways to get through that problem. Or if it's a motivational issue, you have other ways of looking at, well, how can you tweak this work to be able to get you more excited about it? But I think being able to get past the ebbs and flows and the challenges of grad school start to prepare you for kind of what those challenges could be after you graduate. And so being able to seize those opportunities and recognize that by being able to persevere through those challenges, you're actually building yourself up to be able to handle some of these bigger challenges that might come down the road.
I'm going to ask a question of you, which I don't think I've asked of anybody else.
Okay.
Since you did achieve at a fairly young, many of the laureates did achieve at a fairly young age.
Okay.
But what about challenges of success? Mm-hmm. Have you seen anything where success has changed the way that you work or made things more difficult?
Yeah, that's a good question. So some things that are kind of interesting is, so an example is, I was humbled to receive a MacArthur Fellowship. So as a MacArthur Fellow, you get this incredible amount of freedom with what the funding provides, but also this incredible amount of credibility. And I always told people, everybody I interviewed with, or all the students, anybody I worked with, I'm the same person before and after I got the MacArthur Fellowship. But for some reason, the day after the MacArthur Award, I had this instant credibility. Emails that I had sent to people that never got responded to, instantly got responded to. I remember a week later, I got an email from the Secretary of Energy at the time to go have a meeting with the Secretary of Energy. Whereas emails prior to that, the recognition by the MacArthur Foundation weren't answered, right? But I'm the same person. And so sometimes what happens is that you get this credibility instantly where I wouldn't say I don't have to work as hard, but things are easier. But when things were harder in terms of maybe getting that venture funding or getting that grant or getting that thing that I needed to pitch where it used to be harder, where I was challenged, which made the work better, I think you lose a little bit of that. And so in retrospect, it's like the fact that, hey, it was because those papers got rejected a couple of times actually made the work better. Because that grant got rejected a couple of times made that research better. And so I think sometimes you take that for granted, is that instant credibility is great on one hand, but sometimes it makes things a little bit easier where you actually lose that opportunity to make something more rigorous where you would have otherwise. So sometimes I might not think about something in a unique way because it was too easy. But that's something that I've reflected on. And it's like, sometimes it can actually be kind of too easy sometimes.
How do you keep challenging yourself then? How do you face that?
Yeah, it's a good question. I mean, I think the way to do that is to make the problems harder. So I'm tackling healthcare right now, which is one of the hardest problems one could ever tackle. And it's not, and the reason why it's hard is healthcare is not just a technical problem. It's a political, societal, there's a policy angle, there's a regulatory angle. So there's these kind of confluences of things that have to come together to solve that problem. And so by making the problem harder, I think that's how I'm being able to push myself, because I know technology by itself is not going to solve healthcare. There's a lot of other things that need to come together. And by dabbling in these other areas, I think I'm really challenging myself to say, hey, healthcare is hard. Technology is actually enabling some advances, but hey, I'm not moving the needle yet because I got to solve these other things. So I think that's the other thing, is to try to figure out how to expand the scope of the problem quite a bit.
Which sounds like what you were talking about earlier with your advisor, just having that cross disciplinary approach to things.
Exactly. Yeah.
And that segues quite nicely into the HLF actually, because it is both mathematicians and computer scientists, which of course isn't as broad a range as your advisor had, but it is a different experience. It's only Monday of the week, but what has your experience been so far?
Yeah, it's and it's interesting. Yes, it's math and computer science, but the fields have advanced so much. There's so much already breadth there, right? In terms of the kinds of things that they're using their mathematics or their computer science knowledge for. So it's really interesting on what they're applying it for, all the kinds of use cases. Beyond healthcare, you see a lot of it, but beyond healthcare, it's looking at sustainability issues, looking at climate change, and looking at a bunch of different other knowledge bases that they're bringing in, which is kind of fascinating. So, but it's interesting also seeing kind of the clusters of activities too, right? It's the convergence. So, you have a group of people that are super interested in natural language processing, or some people that are really interested in complexity theory. So it's interesting how you have these communities within HLF that you're seeing them band together, but then the communities talking to other communities in this intimate kind of setup where the communities are actually making progress on kind of collaborating across them. So I think it's a fascinating way of getting cross-pollination across not just within computer science, but between math and computer science. But I think, but I'm already seeing the breadth beyond math and computer science in terms of them bringing in domains that are benefiting from math and CS. So I'm seeing more of that, which is a great signal.
Now, I know that it's only Monday, but did you see anything in particular that really just made you go, oh, wow, I didn't think of that, or anything like that?
Yeah, and one of the things is that, having different perspectives is always the best thing, so having a diverse set of perspectives allows you to think about a problem more holistically and differently. And it's just interacting with students that come from different countries that have might have different societal problems, or might have different regional problems or different regional priorities, are always fascinating. It's like, wow, I didn't know that was a major issue, right? And so, but them bringing those problem domains allows us to really think about the things that we're building. How could we adapt it so that they're more generalizable? So a lot of it have been that students have been really clever use cases and applications of what they've done. And so that's been the other thing, is that they've done a great job of bringing some of the regional concerns and challenges here to use this forum as a way to evangelize their problem in a way that people can start to solve those problems. So that's been really great.
Okay. Anything else you'd care to add?
I think one of the things that's great is that, for me, the reason I'm a professor and I'm in this field of research is mentorship, right? So I was lucky to get great mentorship, but passing it along is probably the most rewarding thing. Papers are great, companies are great, you can have great impact with that, but I think when you enable one's career, I think there's no much more rewarding than that. And so I think that's what HLF really enables, is to do that at a massive scale. I have over a dozen graduate students, and I teach a number of undergrads and grad students in the classroom. But when you can enable one's career that you may not otherwise have interacted with because they're not at your university or at your conference, I think that's even more rewarding. And so I think that's the thing that's really exciting. I'm glad that the laureates are able to participate and do participate, because that's probably one of the most rewarding things a professor can do, is enable one's career. And this is just another way of doing that.
Well, thank you. Thank you.
Thanks.
It's been great.
Yeah, awesome.